my colleague Rachel. So Rachel.
Thank you, Nathan, and thank you all for joining us on our seventh Water Wonks of this year. We're really excited to have Daniel Perry present on 2D modeling for flood risk planning of San Antonio's Westside Creeks. Daniel Perry is an ecological engineer with the San Antonio River Authority, or water resources civil engineer, with over 7 years of experience helping communities understand and manage flood risk. His work has supported flood risk planning and mitigation efforts throughout the San Antonio River Basin and throughout South Texas. So we're very fortunate to have him here this morning, and he is going to talk a little bit about enhancing flood risk management for San Antonio's Westside Creeks, including the Apache, San Pedro, Martinez, and Alazan Creeks. And then he'll discuss floodplain management, flood risks, and FEMA's role in regulating the floodplain boundaries and development. So I think that's a pretty brief overview of what you're going to talk about, Daniel, and I'm really excited to learn more about. So I'll kick it over to you.
Awesome. Thank you, Rachel. Like Rachel said, my name is Daniel Perry, and I work for the San Antonio River Authority, and I'm an engineer at the River Authority, and mostly focusing on water resources and floodplain development. And this presentation, I'll try to go a little bit into FEMA's floodplain development and the reasoning behind it, and kind of how their role in floodplain development, and then kind of get into our 2D modeling purposes of the 2D model and what we developed and show some of the results. So FEMA creates a lot of our floodplain maps using computer models that are going to simulate how the water moves during these storms. And a lot of them, the maps are developed using hydrologic and hydraulic studies. So I like to think of it as putting your sock on before you put your shoe on. So HEC-HMS is our sock. It's used to develop and figure out how much rain turns into runoff. So the model looks at things like how hard it rains, the shape of the land, soil types, and how much of the area is covered by pavement or vegetation, or specifically the land use of the area. And it ends up estimating how much of the water will actually flow into the streams and rivers during the storm. So the main purpose of the HMS model is to calculate the flows, and those flows are then put into the HEC-RAS model. So the RAS model is the shoe, and it basically takes those flows and it sees, or it calculates, how the water will move through the rivers and creeks and low-lying areas. It shows where the water will go and how deep it might get and how fast it'll flow. So the main purpose of RAS is developing the depth of the floodplain and the speed of the floodplain. It can calculate other aspects, but the main purpose that we use for floodplain mapping is the depth and the velocities. So by combining these tools, FEMA can identify areas at risk of flooding, some floodplains, and help communities plan better development and stay safer. So just to give you kind of a perspective, this image up in the right here, that's the HMS model, and that's where we're putting in land use data, soil data to calculate hydrologic flows. And we use those flows from this HMS model and try to incorporate it into our 1D hydraulic HEC-RAS model. And so this HEC-RAS model, just to kind of show what it's doing here, this blue line here is the river reach, and all these green lines are river cross sections. So this model is doing a 1D calculation from upstream to downstream, and what these cross sections are seeing is the terrain that we're applying to each individual cross section. They aren't seeing the terrain in between them. They're interpolating from cross section to cross section, and we're trying to place them at very obvious areas of terrain changes. So after FEMA uses these computer models like HMS and RAS to figure out how much of the water will flow during a storm and where it'll go, they end up using this information to create flood insurance rate maps. And these maps are very key in regulation and making sure the community tries to limit development and also try to help prevent development or redevelopment in a way that can be hazardous to the homes in that area. So these firms, the flood insurance rate maps, show areas that are likely to flood, and those areas are called special flood hazard areas. Most of the time, they are the 1% chance of flooding in any given year, or what we call the 100-year floodplain. So this blue area in these images are considered the 100-year floodplain. The maps also show something called the base flood elevation, which is an estimated height that floodwaters might reach during that type of storm. So knowing this BFE can help communities decide how to build the homes or any other structures to reduce flood damage. And it also impacts, depending on the elevation of those homes, it can impact the insurance rates and local building rules. So just to kind of give perspective, the firm here is on the right, and then you have this flood hazard information legend down in the lower left corner. That kind of gives you perspective on the flood zones. And then the cross sections themselves are these black lines, and the elevations, the 702 and so forth feet, are the elevations of the 100-year storm. So if you were to try to rebuild a house in this area, the community may ask you to specifically try to elevate your home to get out of the floodplain. And now this doesn't necessarily mean that you're out of harm's way, but it does mean that there is a likelihood your home won't get flooded if you put it on piers and raise it out of the floodplain. And that's specifically for the 100-year storm event. So FEMA's modeling helps create these maps and guide smarter buildings for these safer communities. So building on those flood maps that show the special flood hazard areas and base flood elevations, flood zones are specific areas identified as having some level of flood risk. These zones can help communities understand where flooding is more likely to happen, and it really varies on the type of flood zone that is identified. So a lot of our regulations and safety rules focus mainly on the 100-year floodplain, which is an area with a 1% chance of flooding every year. So that means even it may not flood every year, there's a significant chance it could flood. And so I know a lot of people hear 100-year floodplain and they think to themselves, this is a chance of it happening once every 100 years. And that's not necessarily true. I like to think of it as a 100-sided die. And every time it rains, you can roll that die and maybe it'll hit the 100 and it'll actually rain the 100-year floodplain. And that die can be rolled every time it rains. So you could have the 100-year floodplain twice in 1 year. You could have it twice in 50 years. It just depends on the probabilities of that specific storm. And we're seeing the flood statistics change as we get more and better data. So these flood zones specifically guide how and where buildings can be constructed to help protect people and property from flood damage. And again, the 100-year is the main flood that we see FEMA and communities regulate to. And so in San Antonio specifically, we're going to see a couple different types of zones. I'm just going to focus on the major ones that you'll see if you end up going to see a firm or a floodplain from the NFHL layer. But specifically, we see a lot of Zone A, which is the blue in the previous slide. You see this blue floodplain. It's a Zone A or AE. So if it weren't to have base flood elevations or BFEs, that means it's a Zone A. That means it's less detailed and it doesn't have structures in that model. But if it were to have those base flood elevations like we saw in the previous slide, that means it's a Zone AE and it's a more detailed model. So it includes structures, it includes bridges, it includes culverts, and that gives us more confidence in the accuracy of that floodplain. We also see a lot of Zone X floodplains throughout the area. So the city, they like to show the 1% future floodplain. So you can see that in this legend, the gray and dashed image, that's the 1% future conditions. A lot of other entities like to show the 500-year or the 0.2% floodplain, which is this orange area. So there are a lot of different floodplains that they show on this map, but majority that we see in the city, in Bexar County, are going to be Zone A, Zone AE, and future conditions. So flood insurance rate maps are important tools that can help our governments create rules for building permits or codes. And these rules can help make sure new buildings are designed to reduce flood risk. Firms also support the National Flood Insurance Program, or NFIP, which provides insurance for people who live in flood-prone areas. So this is very important. And a lot of these communities, they need to make sure that they're enforcing the rules of the special flood hazard areas to keep receiving support for this NFIP program. And the enforcement helps protect residents and property from flood damage, but also keeps insurance available and affordable for the people that do live in these floodplains. So just to give perspective on what the NFIP actually has given to people, in 2024, it paid over $7 billion in claims nationwide, and that was $156 million to Texas alone. And as you can see from the image, there are a lot of communities that participate in the NFIP program. We also to give even more perspective, the July 4th flooding that happened throughout Texas, there's an estimate of around $18 billion needed for the assistance. And that can combine the disaster declaration assistance, but they are going to take money from the NFIP, which is coming from these communities and people that are paying for this insurance. And it's important also to know that a lot of these rules, they may not be enough to match today's reality. A lot of the rules in the past definitely don't match today's reality, and it may not match the rules in the future. So it's important to make sure that we're enforcing these rules and preventing these developments in high-risk floodplains, because the developers aren't necessarily the people that are going to face the risks or face the payments. It's going to fall on the people that buy the houses. So while firms are useful for showing risk from river and stream flooding, which we will call fluvial flooding or flooding from channels and rivers, they don't really show risk from pluvial sources. So flooding, overland flooding, urban flooding caused directly from heavy rainfall and runoff that doesn't actually follow natural river channels. This type of flooding is often not included in the firms. Because of this, flooding can sometimes happen outside of the SFHA or outside of the flood hazard area shown on the maps. This means it's important for communities and property owners to be aware that flood risk can exist even in areas not officially mapped. And so this is another important slide of kind of showing the differences. So we have our 1D HEC-RAS model showing just the fluvial channelized flooding in this top right image. And you see it going along Apache Creek here. You see some of it leaving the channel, but overall it's channelized flooding of an identified flooding source. But if you look at the bottom left image, you start seeing our 2D model, and we start having the model project area covers the entire area of the Westside Creeks. So you start seeing where a lot of flooding may come from, and some areas that we may not have identified previously through FEMA maps. And a lot of FEMA maps, they're created to regulate floodplain development. Sometimes you need these 2D models to help mitigate flooding in general. So since flooding can happen from both creek and river overflowing and the urban overland runoff, it's important to look at the whole watershed when planning for flood risks. A watershed approach considers all sources of flooding across the entire region, not just specific to river channels. This encourages different local governments and agencies to work together and leads to better planning and stronger, lasting solutions to reduce flood damage. The approach supports both building physical structures like channels and detention ponds and non-structural actions like better land use planning and nature-based solutions, specifically leaving wetlands and natural areas alone and letting them absorb floods as best they can. Overall, this approach can help us create a safer and more resilient community. So we're trying to identify a holistic approach. When we just have these 1D floodplains, we don't really identify where the flooding may be coming from. And so if you have these 2D floodplains, you can have a better idea of the whole watershed and identify where the flooding may come from, and try to have this multi-tiered approach of flood resilience. So just some examples of structural solutions and non-structural solutions. Some of the structural solutions we may see are channel modifications, so widening and deepening channels to carry more floodwater. Stormwater management system, so like drains and pipes, and then creating bigger drains and pipes to have more storage and move that water to the channels or the rivers. And also detention ponds, which are big ponds that can store the water and then slowly release it into the rivers and creeks, so that peak of water isn't as high over time. Also, there are different ways to elevate homes, flood-proof homes, and you can also incorporate dams to try to have some structural flood risk solutions. Non-structural solutions can include floodplain zoning, which limits the development in flood-prone areas, which is what FEMA is trying to do. Early warning systems, which alert people to areas that are prone to flooding and low water crossings. You can also have community preparedness, like education on flood risks, turn around, don't drown, making sure you know where your house is comparatively to a floodplain, or even when you're camping comparatively to a floodplain. And also nature-based solutions, so like the wetlands and the natural areas to absorb the floods. So when you build upon this watershed approach, a 2D model could be a powerful tool that helps simulate how water flows over land surface during the storms. Unlike the 1D models that only looked at river channels, 2D models can show how runoff moves across the streets, across fields, around buildings, and in the urban area in particular. And it's not just urban areas. You can do a 2D model in all areas, but it really is helpful for urban areas, especially for flood mitigation. These models can also include how water interacts with things like roads and bridges and storm drains. And for our Westside Creeks model, we weren't able to incorporate storm drains. We used HEC-RAS, which at the time didn't have storm drain in the model itself, but we do hope to start incorporating it, and it will show a decrease in the floodplain when we do incorporate it. It may show decreases in the urban area, but that could also mean increases along the channel because that's where a lot of the storm drains are going. This gives a much clearer picture of the flooding across the whole area and can help communities plan better and design more effective flood protection. So 2D models are ideal for identifying risk and mitigation options where structural control may not be viable. So maybe we can't put a detention pond. We can't widen the channel anymore. So when we start seeing these 2D models, we can identify other areas. We can put other control measures or mitigation measures. By capturing all the flows, 2D models can improve flood risk analysis and help communities develop stronger coordinated plans to reduce flood damage throughout the entire watershed. So using these 2D models can support a more effective flood control strategy that work together across all the watershed. And planners can design detention areas that hold flood water, diversion routes that redirect the water, and green stormwater infrastructure which could be natural engineered systems that manage the river water where it falls by absorbing, slowing, or filtering the runoff. And these GSI examples include rain gardens, green roofs, permeable pavements, bioswales, and many others. And it really does help not only reduce flooding, but also improve the water quality throughout the area. And San Antonio does have an issue with water quality throughout our creeks and rivers. So it's multifaceted. It could be multifaceted benefits. So some examples of some of these green infrastructure, one of them is this World Heritage Center bioswale. Just to get into what a bioswale is, it's a ditch, basically a shallow ditch where when it rains, water flows into it and the plants and the soil can slow down that water and soak it into the ground. It can help reduce flooding, but it also can help filter out dirt and pollution before it actually reaches the rivers or storm drains. And this is important because not only are we trying to limit flooding, we're also trying to benefit our water quality in the area. It also can be very aesthetic. You can include natural occurring plants or plants that are from the area in these bioswales and make it environmentally friendly. Some other examples are along Lower Broadway. So we have our bioretention area and our permeable pavers. Bioretention is very similar to the bioswale here. But it's a smaller land area. So it also is designed to collect and absorb rainwater, and it uses the plants and the soil and the mulch to filter out the pollutants and slow down runoff while cleaning the water. But it also helps the flooding if you were to put these in line and in a lot of areas throughout the city. Permeable pavers are also paving stones or blocks or even permeable asphalt that has small gaps or porous surfaces that let the rainwater soak in instead of running off. And we have a lot of asphalt and concrete in the city that just, instead of allowing the water to soak in and get to the aquifer or get to groundwater, it just goes off and ends up filling up our streams and rivers. And this can help. Permeable pavers, bioretention, and all the green infrastructure can really help reduce flooding if used in mass to allow water to seep into the ground and also help benefit the water quality of our city. So just to be aware, these are very helpful mitigation efforts that 2D models can really help identify areas where these can be placed. So just to summarize the general idea of FEMA's floodplains, they use these models to map the floodplains. These maps guide the building rules and insurance, but mainly focus on river flooding, on riverine creek flooding. Flooding from heavy rainfall runoff or overland flooding and urban flooding is often missed. So we need to make sure we're looking at a watershed approach that looks at all the flooding sources and encourages regional collaboration. Advances in 2D modeling also show how water moves across the land and around buildings and supports smarter flood control methods like green stormwater infrastructure. So while the FEMA maps are very helpful and the more accurate they are, the more helpful they are, they don't always show the full picture of flood risk, especially in urban areas. So by using the 2D modeling, communities can get a better understanding of how floodwaters flow and also get some extra insight that helps planners create smarter and more resilient protection plans for people and property. And so again, this is a good example of the differences between 1D and 2D. So in 1D, you have this single floodplain that was identified previously. So we build our models off of that floodplain specifically. In 2D, your project area can go all over an entire subbasin or watershed. So you can start seeing floodplains and where the flooding is mainly coming from. So you see the flooding goes north of Hildebrand and some flooding comes from the east. So you can start using this information to input some of these green infrastructure or some of these detention ponds or other channels to make sure that you're slowing the water down or preventing it from getting to the channel that is causing the majority of the flooding. So with all this understanding, of how 2D modeling can help improve flood risk analysis, we can look further into the Westside Creeks 2D modeling project and how it can help the community plan for safer and more resilient flood management. So the Westside Creeks, they're in the central portion of the San Antonio River watershed near the headwaters of the upper San Antonio River subbasin. They're within Bexar County, obviously, and on the west side of San Antonio. And all the creeks feed directly into the San Antonio River south of downtown. So our project area, even though it's a very small portion of the San Antonio River basin, it's an important area for understanding mitigation actions, especially in urban areas and future risks. So the Westside Creeks, just to dive into a little bit more, they're made up of four main streams: Apache, San Pedro, Martinez, and Alazan Creek, and they convey about 45 square miles of highly urbanized watershed, which produce flows of around 60,000 CFS during the 1% rain event or the 100-year rain event. And just to kind of give you perspective, the average, and when you're floating down the Comal, that flow is around 300 CFS. So we're talking about 200 times the amount of flow coming through San Pedro Creek south of downtown whenever you have that 100-year rain event. So our project limits for this project are north of Woodlawn Lake and Elmendorf Lake, and they contain a little bit of Martinez Creek and San Pedro Creek. And just to have more perspective, this area has been a part of San Antonio for a long time, with a lot of the development happening in the late 19th century and early 20th century before they had floodplains, before they had awareness of where to place homes. So this area has been urbanized for a really long time, and that's why we have to be kind of reactive in our mitigation strategies. So the river basin has been in the lower section of Flash Flood Alley, and it's very susceptible to rapid, severe flooding, which I think we're all keenly aware of, especially now. This is due to the Balcones Escarpment. It's basically a very steep hill country terrain of the escarpment and down to the kind of flat terrain south of San Antonio. And combining this with the major storms due to the moisture from the Gulf, This produces rapid flooding throughout the region. This has led to a lot of extreme flooding events throughout the hill country, throughout Texas, and in the San Antonio River Basin, but particularly in the Westside Creeks. So due to its location in Flash Flood Alley and being very urbanized very early, the Westside Creeks have a long history of damaging flooding. One of the most influential floods was the flood of 1921. This destroyed a lot of the residential communities in the area within the Westside Creeks and in downtown San Antonio, mostly due to the poor development practices and inadequate maintenance of the tributaries on the west side. So for the event, there was around 7 inches of rain that occurred overnight, and the creeks over or flooded, and it actually ended up having about 80 to 200 plus lives lost, depending on the sources that you're looking at. The flood actually triggered the construction of Olmos Dam, which was completed in 1927, and Olmos Dam really does help with the flooding in the area. It also triggered in 1954 the construction of the San Antonio Channel Improvements Project, which the Army Corps and the River Authority helped construct. This project was around 31 miles of channel improvements on the west side, and also included the two tunnel inlets from the San Antonio River and San Pedro Creek. So we have two tunnels going underneath the city, basically to help with flooding. The Westside Creeks Channel Improvement Project was actually completed in the 1970s. And you can go see a lot of the channel improvements. It's basically wide, deep channels, and a lot of it not very natural, and a lot of it is concrete channels. So even with these channels and even with the dams, we still see flooding consistently on the west side. So the River Authority, we've been a technical partner with FEMA for a really long time, developing projects that include hydraulic and hydrologic studies of the areas. One of the studies we utilized for our 2D modeling project was the Upper San Antonio River Study, which we initiated in 2019 and used updated statistical analysis of historical rainfall data and updated terrain LiDAR information. So just to give you all a little bit more information on what LiDAR is, it's a technology that uses light to measure the distance between a sensor and the ground. And that sensor is usually in an airplane flying over the watershed or the county that you're trying to look into. And that develops a terrain model that we can incorporate into our 1D models and our 2D models. And it's very important. The better this LiDAR data gets, the better our modeling is. So that it's important to make sure that we're getting good LiDAR data. Another study we incorporated and compared to was the Texas Water Development Board Upper San Antonio River 2D base level engineering model. It's a simplified model that was completed in August of 2022. Since it's a BLE study, a lot of the information wasn't present that we incorporated into our Westside Creeks model, specifically structures. And structures play an important role in flooding. They can really back water up at times. Also, the BLE model was a coarser mesh. So the mesh of the 2D surface is a lot of square grids, and their model was around 200 by 200 square grids throughout the entire area. And this was due to it being a very large area and trying to reduce run times. But overall, it's less accurate when you start compared to smaller grids. Even with it being lower detail, we felt like it was important to compare the floodplain, especially since we don't have a lot of 2D modeling in this area. And we wanted to compare the less detailed Water Development Board model versus our detailed Westside Creeks model. So we had a lot of objectives of this project. First, we wanted to develop an efficient approach for preparing existing hydrologic and hydraulic models to support FEMA's future modeling needs, documenting any of the challenges or recommendations for these future efforts. FEMA's modeling needs for the future is going to go from 1D to 2D, and we want to make sure we're prepared and we're efficient whenever we end up having to go into that role. One of the questions we wanted to answer with this effort was how we can effectively leverage work from past models and modify and transfer that data into 2D modeling. We also wanted to understand the feasibility of converting our existing 1D model inventory to 2D. We have a lot of 1D models. We created a lot throughout the entire area, and we wanted to make sure all that work we don't have to recreate when we do the 2D analysis, which I think we learned a lot from this project. Another objective was to develop a detailed 2D data for this area. So we had 3 different scenarios. I'll talk about that more later. Lumped hydrology, rain-on mesh with losses in HEC-RAS, and rain-on mesh with losses in HEC-HMS. So we wanted to document any of the challenges and benefits of the approaches we evaluated, as well as other observations. And we also wanted to make sure we develop a flooding depth and velocity grid for the area so we can see depths of the floodplain and how fast the floodplain is moving. We also wanted to provide analysis of the results of each scenario and comparisons between each approach, along with comparisons between the 2D BLE and detailed 1D models for the area. And different approaches may be better for different scenarios of mitigation. So we wanted to make sure we're aware of that moving forward. From the data types that can be extracted, we wanted to see how the flooding looks in Westside Creeks for each of the scenarios. So our final objective was to identify future precipitation impacts throughout the Westside Creeks, which will help identify future planning areas of concern. Our goal was to apply worst case future climate precipitation data for the 100-year storm event, for the 20, 40, and 60-year time horizons, and see the impacts on flooding depth compared to the existing climate. So results can help identify how we leverage future flooding impacts into the community regulations and codes and avert development within these higher future risk areas and mitigate for future flooding. So we can both see where we can mitigate for flooding, existing flooding, but also see where these areas might have higher chances with the future rainfall data. So just to give you all a little bit of perspective on the model itself, we built the model to see how the water moves across the urban area. The model shows how the water moves in 2 directions, across and along the ground. So 1D, we're going from upstream to downstream, and 2D, we're trying to see how it spreads, basically. It has a better calculations to see how it spreads. This, especially in flat and urban areas. The land is divided into a grid of small squares, as you can see in this image to the right here, and it's like a checkerboard. The model uses the grid along with the elevation data, which is what you can see below that grid, the green to red to white and gray, and rainfall data to simulate how the water flows. So we divided in this area. We did some sensitivity analysis from 200 by 200 to 50 by 50 grid cells, and we ended up choosing the 50 by 50 grid cell to give clear results, even with the longer runtime. So larger cells will have a shorter runtime, but for a BLE model, that can be a runtime of 8 hours to 12 hours. Where we're comfortable, smaller cells, an hour to an hour and a half runtime for the Westside Creeks area. So if we were to go larger, maybe it would create much longer runtimes, but we were very comfortable because we wanted to make sure we were capturing the risks better. We also included over 70 bridges and culverts to reflect how the water flows through those bridges and culverts in real life. And that was an important part of our development. So we use this same geometry for every flood simulation to make sure we keep the results consistent and easier to compare. So we were able to use the 1D data and automate adding all the bridges and culverts into the flood model, making it a much quicker and easier setup. So we were able to make that an efficient setup, moving our already developed 1D structure data into the 2D models. And we did this and then we ended up running the model for all 3 of our scenarios. Just to go into those specifically, our lumped hydrology, that is the most analogous to our 1D hydraulic model. So basically, we're applying flows from HEC-HMS directly to the 2D channel. And the 2D model in that instance really shows split flow locations a lot better. We also did rain-on mesh with losses in HEC-RAS and rain-on mesh with losses in HEC-HMS. So for rain-on mesh with losses in HEC-RAS, we're applying rainfall directly to the grid and then accounting for all losses such as infiltration and storage in RAS itself. So rather than doing HMS and then RAS, we could just put precipitation on the grid, incorporate all that loss data into RAS, and then run it and see how much the rain turns into runoff and how it flows throughout the landscape. Rain-on mesh with losses in HEC-HMS is very similar to what we do in 1D. We get all our losses in HEC-HMS, but instead of grabbing the flows from HEC-HMS, we're getting what's called excess precipitation. And so that excess precipitation is what we're applying to the 2D grid in RAS. And we wanted to see, again, this was more about seeing the efficiency between the two and the accuracy. And we ended up finding out that RAS and HMS or the radar mesh with RAS or radar mesh with HMS weren't very different from each other. So it is a lot more efficient to use radar mesh with losses in HEC RAS, so you don't have to use two different programs. By trying these different amounts and patterns, we found a lot of areas that were most at risk from flooding, from pluvial flooding, from overland and urban flooding. But we also looked at future precipitation changes to see how flood risk might increase and try to help communities prepare better for future existing floods and future floods. And so here's a slide for our results, and you can see the differences pretty drastically between the two. We have our rain-on mesh with RAS in the left here. As you can see, it's a lot of flooding, and I just want to preface this. This is showing all flooding that's happening, so it can be less than an inch at times. But it is important to understand there are a lot of areas that are missing, that are included in that show pretty deep flooding, included in this rain-on mesh model compared to the 1D and compared to the lumped hydrology. And so on our right here, we have the lumped hydrology model, which is applying flows directly to the channel itself. And so this is very riverine, very fluvial flooding. And you can see that the model does show floodplain going outside of the channel a lot, but it also is showing very 1D flooding. So it may not give a perfect perspective of flooding throughout the urban area, but it does allow us to at least see the split flows a little bit better. But the rain-on mesh with RAS is really showing a good difference between and showing where the urban flooding can be coming from and where we might be missing flooding when we're looking at these 1D models. So there are a lot of benefits for 2D. It's a flexible and easy model to update with any new rainfall data, which is what we did with this future rainfall information that we had. So all we had to do was grab the future rainfall hydrographs and incorporate it into the model and run it, and then we can see the differences. It lets us quickly see how the changing rain patterns might affect flood risks over time. By adding all these future scenarios, we can better understand potential flooding and find ways to reduce risk and improve infrastructure. In places like the west side of San Antonio, where it's very urban and flooding is complicated by buildings, hills, and roads and roofs, the model helps planners and engineers really prepare for flooding today from areas that we weren't fully aware of and for future floods. It supports long-term planning because it can be updated regularly and improve flood protections with little disruption. Looking ahead and understanding this changing rainfall, though, is key to managing flood risks in the future. So we wanted to use the model to look at future rain data that helps us plan better and keep flood systems strong as conditions change. So to develop a lot of these future impact models, we needed to understand future hydrologic trends in the river basin. So from previous studies, the assessment evaluated statistics for 2 different climate scenarios and 3 different time horizons, the 20, 40, and 60-year time horizon. When comparing projections for the 1% annual chance event across all the counties, the analysis estimated about a 22 to 36% increase in precipitation intensity in the 60-year future. These, in turn, incorporate increased peak flows of around 48 to 49% for the 60-year future. So just kind of to visualize it a little bit more, for the 24-hour 100-year rainfall event, right now our existing Atlas 14 is around 12 to 12.4 inches in San Antonio. And for the future climate in 60 years, we're seeing that increase to around 15.4 based off of the data that we were looking at. This, in turn, intuitively increases the width and the depth of our floodplains. So this is a good example of what we're seeing, our existing floodplains look like, and the potential future 60-year floodplain looks like as we see our rainfall intensities grow. And we can see about a 390 acre acres of land can be added to the 100-year floodplain. So as you can see here from this image, I think it does a really good job of explaining the existing floodplain is this light blue here, and you can see the growth over the years to incorporate a lot more land in the area, and in turn, a lot more houses and a lot more risk. So that slide was a lot of fluvial data. We were just looking at riverine risk. There is also significant risk from overland flooding or pluvial flooding. Some of these areas can see depths of around 1 foot increase in these future climate scenarios looking at the data that we were evaluating. So you can see here, this image is comparing our 60-year rain on mesh RAS model runs in our existing model run. And you can see areas that are pluvial that are showing about a 1/2 foot to 1 foot of increase. And it's, again, important to understand where these potential areas are. And also those areas feed directly into the channel where you can start seeing 3+ feet increases in flooding. So just to summarize everything, it's very important for us to know that FEMA and their 1D floodplains, they are very important, and they help prevent flood development within the floodplain, but they also don't necessarily show all the risk that's involved. So it's good for us, and it's important for us to start developing these 2D modeling to have a more clear perspective and try to have a holistic approach to these flood mitigation. So I'll just pass it back over to you, Rachel. I'll be here for any questions. Thank you.
Okay, so thank you, Daniel, for that. I appreciate it. So we are going to turn into the Q&A function. It's 4:12, so we got about 15 minutes for Q&A. And let's see, looking at the chat right now, it looks like Ethan G, throughout the portion of today's conversation, put out lots of information regarding permaculture techniques, berms and swells. Looks like some screenshots of a presentation he presented out before, mentioned about rain gardens, and looking like more detailed information about bioswale design. So thank you again for sharing that, Ethan. I would also mention regarding low impact development that GIA has a low impact development manual that is readily available on our website that we can get a copy of also for this chat. So first question I have is from Cindy C, and she's asking about, does widening a channel also reduce riparian area and vegetation?
So I haven't been working a lot in flood or channel design, but you can see in these channel modifications, they are going to reduce this riparian area. It just depends on whether or not on how you're designing the channel. A lot of the times in San Antonio, or what we are basically we're mowing the channel and we're putting a lot of concrete in these areas. But we do try to do a lot of stream restoration techniques. So you can widen the channel, but you also keep that foul wag in the middle there, and you try to really make sure you're keeping that area as natural as possible with the correct the natural vegetation of the area. But yeah, a lot of the time, especially when you're just considering flooding, it does end up reducing the vegetation and sometimes the riparian area.
Thank you, Daniel, and I hope that answered your question, Cindy. So the next question I have is from Kenneth, and he's talking about, let's see, he's asked, Hill Country FEMA maps often do not exist. What can we do to get, and he mentioned Blanco County for this example, Blanco County maps completed for the rivers and the tributaries?
So Blanco County is out of the San Antonio River jurisdiction, but you should be able to see a lot of these maps on the NFHL layer, on FEMA's NFHL layer. So I can try to show that really quick. I do have that. Let me try to back out of this. I do have that pulled up, so I can try to
Okay.
show it. So FEMA's National Flood Hazard Area. I just wanted to kind of point out what some of the stuff we see in in the city itself, but you can go to Blanco. Hopefully I'm going the right direction. And you can zoom in. I'm trying to find Blanco. It's a little bit north. So maybe some of these areas may not have floodplain mapping available through the NFHL layer. So you would want to contact the floodplain administrator for that area. So Blanco County would have a floodplain administrator, and so would the city of Blanco. Um, but there's also BLE viewers for the entire uh, state of Texas right now. So you can go to this estimated BLE viewer and you can start seeing floodplains in this area. Now, those aren't necessarily they aren't regulatory necessarily, but this NFHL layer should help you kind of identify what the floodplain looks like in that area. So I can try to find Blanco specifically, but we can go to the next question really
Okay.
quick.
Thanks for that. And Kenneth, hope these resources and tools are helpful for you. Let's see. The next question I have is actually from Rachel. She is asking about, do you know in the FEMA floodplain map exclusion process, when property owners are requesting to be removed from the hazard area, is that process directly between the property owner and FEMA? So that's the first part. So we'll leave it at that for the first part.
So it really depends. You have to go through a LOMR or a LOMC process. In that, so sometimes it could be directly from FEMA, but most of the time you're dealing with the floodplain administrator of your county or your city. So that's probably the first person to go to see what you can do. Sometimes you have to give elevation certificates or develop elevation certificates. So like survey your area to show that you're outside of the floodplain. But other forms can actually be developing a hydraulic model to show whether or not your property is outside of the floodplain.
Okay, thank you. The second part is asking about, does the river authority or any local government or state agency have the opportunity to weigh in or make recommendation on those requests to FEMA?
So yes, we review a part of the river authority. We review LOMCs. That doesn't necessarily mean we review the elevation certificates, but if a developer were to build near or in a floodplain, we review. They have to go through a process and get a floodplain development permit from the city or the county, and then we go through the process of reviewing that modeling to make sure it's accurate and it's feasible. So we do go through that process of review. It's not for everything and it has to be within our jurisdiction.
Okay, thank you for that. And Rachel, hopefully that answers your question. I appreciate the back and forth, Daniel. Thank you. Next question I have is from Rob. Rob is inquiring about, in addition to incorporating predicted changes in rainfall, are you also considering planned or anticipated developments in the area?
Yes, so a lot of the future rainfall data that is specifically based off of future land use. So a lot of these areas that are highly urbanized, we don't really see a large change between what's uh, there today and what the future is. So a lot of that future land use, whenever you start seeing the 100-year and the 100-year future change, it's in these rural areas where we do really anticipate lot of suburbia kind of getting out there, kind of like in the Alamo Ranch area of San Antonio.
Okay, thank you for that. The next question I have is from David. And David's asking, how do these 2D models correlate to the 500-year flood maps?
So we didn't look at the 2D models when we were looking at or we didn't look at the 500-year floodplain when we were looking at the 2D models. So I'm not 100% aware of that right now. Our base level engineering models, they do show the 500-year floodplain. And again, you can go look at that from this FEMA um, base level engineering viewer. So there is data in there where you can actually look at flood depths for the 500-year. But we didn't, for this study, we didn't really incorporate or compare the 500-year.
Okay, thank you for that, David. Hopefully that answered your question. I have, let's see, some thank yous and thank you for your presentation from both Cindy and Rob. Next question I have is from Gemma K, and she is asking if the museum reach has a 2D assessment done, and more specifically, she's asking more about the River Road neighborhood, if it has a lot of fluvial risks.
So Museum Reach and Mission Reach don't have 2D models right now,
Mhm.
at least not detailed 2D models. We do have that BLE, FEMA BLE model. So FEMA develops BLE models and the Waters Development Board develops BLE models. So you can go to this BLE viewer and you can kind of look at the types of um, risks that you may have based off of the pluvial flooding. But again, this is very high level. These models don't incorporate the structures. They don't incorporate bridges or culverts. So some of these areas, they may show more flooding. Some areas may show less flooding. But um, this is the 200 year. And then you can see here, this is the 100-year risk. Actually, let me go up to River Road or the Museum Ridge. So up here. But this, again, we have a 1D model of this area, and it's pretty difficult to model a split flow area like this in 1D. So being able to develop this as a 2D model, even though it may not be 100% accurate right now, it's a good path forward to actually understanding legitimate risk.
Okay. Thank you, Daniel. I appreciate that. Gemma, hope that helps for you. I have another question from David R, and we are doing good on timing, so I'm going to take it. David asks, what type of resistance from developers do you anticipate to this 2D approach?
So 2D isn't necessarily going to be used for regulatory anytime soon. I would assume there would be some resistance from developers just because they need to make sure that it's as accurate as possible. And again, it's going to show a lot more floodplain as you can see. But right now, it's not going to be regulatory. The 1D models are regulatory. And we're trying to use this 2D model more for mitigation. And you can start seeing where this flooding gets or where the flooding is coming from before it gets to the channels. And you can start putting a lot of these detention ponds or these green infrastructure along these routes to be able to slow down the flood or flow and kind of sink into the ground better.
Okay. Thank you for that. Let's see. Carl, and just circling back to Rachel's question about the FEMA involvement with the LOMAs, and he just mentioned confirming your point for individual properties, the process
Mhm.
is primarily between the property owner and FEMA.
Yeah, a Loma
Um,
specifically too. Loma
yeah,
is specifically between the property owner and FEMA. Yeah.
thank you for confirming. I appreciate it. Looks like I have another question from Mark K. Uh, would it reduce the fluvial rate of the canalized streams by eliminating concrete and adding natural landscaping?
So the main purpose in concrete, it's kind of an inverse relationship. If you speed up the flow, you're going to start seeing that water surface elevation decrease. So if we were to slow down these flows, you'd have a much wider floodplain. So eliminating concrete, that's great if you have the floodplain to kind of build or to build in or build around it. But when you start slowing down the fluvial rate or the river rate, channelized rate, you're going to start widening that floodplain. And most of these urban areas, you can't really start slow down the floodplain when it's channelized like that. You're trying to prevent the water from actually getting to our storm drain systems and try to actually infiltrate at the source where it is actually raining.
Okay, thank you for that. I appreciate it. There's lots of people saying good job, interesting. Thank you so much for your time. And that is all the questions I have on the chat. I will open it up to open floor, or you can still use the chat feature because we still have about 5 minutes left until we hit the 4:30 mark. So, does anyone else have any questions, comments? I will say speak now, forever hold your peace.
I'm putting the EBFE viewer and the NFHL layer in the chat. We also have at the River Authority, we have our draft floodplain viewer. So we're going through this process of developing new floodplains, and that's kind of what we were incorporating in our 2D model. So we have what we call the effective floodplain. So that's the older floodplain, and then we're our draft floodplain. So you can start looking at the differences between the two and try to look at your area if you would like to, and see what the change potentially can be. And so that draft floodplain viewer, the NFHL layer, it's going to show the effective floodplain. The viewer, it's going to have effective, but also show our drafts.
Okay, thank you for that. I do have one question that just came in, and it's kind of what you and I were talking about right before about the timing of everything. Uh, well, before I get to that, can you go to your last slide? I got a
Yeah,
question about could you show your contact information again
let me
for
jump to
Norma
that.
Jean?
Yes, let me jump to that really quick. I'm trying to show it. I don't know why it's not jumping to it.
Oh no, you're good.
I'll just slide this over here.
Okay, there you go, Norma. That's his email right there for you to get in touch with. So, Camila R asked, "What is your opinion about the camps and camping areas in Kerr County?" And I'm guessing she's assuming more about what the recent flooding implications have happened in that area.
Yeah, I'm trying to be, it's kind of natural for me to start paying attention to that stuff. And in all honesty, I would like to know a lot more information on it before I could actually have a concrete opinion. I have worked with Charlie Hastings up there. He's the floodplain administrator of Kirk County. Um, but it's hard to tell in some instances, if those camps were outside of the 100 years. So you can go look at the effective floodplain, and you can see that some of them are actually not even in the 100-year floodplain. But it really depends. You have to really look at all the data to really have a good concrete understanding of what potentially went wrong. But I think a lot of it could be changed in the future, and they could actually start requiring some of these buildings to be built with buffer outside of these floodplains. They're also potentially going to start developing. I think the floodplains out there might be from 2011 from old LIDAR. So starting to develop better floodplain maps out there, which is very important. But also camps always are along. Now the camps for the kids, those buildings they could be moved outside of the floodplain, but camping areas specifically, a lot of the time they're along these rivers and creeks. So it's important for the community to have these emergency actions, but also it's important for the people that are living in these areas or staying in these areas or camping in these areas to be keenly aware of the flooding that flood potential of especially big rivers like the Guadalupe. Definitely.
Thank you, Daniel. I appreciate it. And it looks like that's all the questions I have. We're about a minute and a half towards 4:30. So I'm going to conclude Water Wonks today. Again, thank you, Daniel, for your time and your presentation. Myself and Gia really appreciate it.
Mhm.
And just to leave y'all off, we're promoting our next Water Wonks lecture series, our number 8 series, which is going to be happening on August 27th at 3:30 p.m., same time and place, the fourth Wednesday of the month. And our lecture is going to be talking about smarter writing, faster research using AI for water work. And this is going to be done by Roxana Dean, who is the president of Comal Conservation. My colleague Rachel posted a link to sign up for that lecture. Registration will open up for that tomorrow. And also, and she posted at the end of the chat, thank you, I appreciate it. And also, we will be getting this Water Wonks up on our GIA website by the end of the week, so people can view it at their pleasure after today's conversation. So it's 4:30 on the dot. Thank you, Daniel, again. And thank you, everyone, for attending today's Water Wonks. Have a great rest of your day, okay?
Thanks, Nathan. Thanks, everyone. Appreciate you all
Thank you.
listening.